A point charge of charge plus q is fixed at x equals 0 on the x-axis, and a point charge of charge minus 2q is fixed at x equals d. Point P is located at x equals 3d. Assume the charges are stationary in a vacuum and let k denote Coulomb's constant. Derive an expression for the net electric field at point P, including both its magnitude and direction in terms of q, d, and k. So first let's sort of draw this problem. So if we draw a line, we know that all of the charges are on the x-axis, so they all lie on the same line. Drawing a line. Okay, that's better. So if we have that this end is x equals 0, then we have a point charge here with charge plus q. And then at some x equals d, where d is just some constant, we have a charge, another point charge, this time with charge minus 2q. So this is minus 2q. And then finally, we're asked to evaluate the electric field at some point x equals 3d. And we want to find both the magnitude and direction. So the magnitude of the electric field is given by the force, is the force per unit charge. So it is just equal to k, which is Coulomb's constant, times the charge q divided by r squared. And then r squared is the distance. So r is the distance between the source charge, which is whatever point charge that you want to calculate the electric field for. And then we want to, it's the distance between the source charge and the position where you're evaluating that electric field. So this is the formula for the magnitude. And let me specify this more explicitly. So the magnitude will be positive, since that's just it's just a number. It doesn't have any directional data. So let's start by perhaps computing the electric fields due to each of these charges, these point charges here. And let's compute the magnitudes. So the magnitude of the first point charge, I'm going to call this point charge 1, and this is point charge 2. So the magnitude of the electric field due to point charge 1 is just k times q, big Q, divided by, and r is the distance between this point here, x equals 3d, and the position of the source charge. So that's just the distance is 3d, and we square that whole quantity. So that's kd, or kq, over 9d squared. And that's the magnitude of the first point charge's electric field. Now let's do the same for the second point charge. It's k, and this q is negative 2q, but we are finding the magnitude, so we don't care about the sign yet. And we divide it by, this time, we need to be a little more careful because we're still evaluating at 3d, but the actual distance is actually 3d minus d, since the point charge is at a position of d. So this becomes 2kq over 2d squared. So that's 2kq over 4d squared, which is just kq over 2d squared. So now that's all of the magnitude information that's done. Now let's figure out what the direction is of these two electric fields. So at this point, we know that if if we have a source charge that's positive, then all of the electric fields will be pointing radially outward from it. And similarly, if we have a point charge with a negative charge, then all of the electric fields will be pointing towards it, and it will be pointing towards the point charge. So based on this information, we can infer which direction the electric fields will be at x equals 3D. So first, let's find the direction of E1. This is the field due to this point charge. It's positive, so its electric field will be pointing outwards in all directions. So in this direction, it will be pointing outwards too, towards positive x. So in that case, it will be pointing towards the right. And then for the second point charge, it's negative. So all of the electric field lines will be pointing in. And at this point, it would be pointing in towards it, so it will be to the left. And now the total net electric field is just the sum of each of the separate electric fields at that point. So we can sum, this is just vector addition, and we can sum it. But since we are in one dimension along the line, we can just use positives and negatives to denote direction. So now let's say that we choose this direction to be the positive x direction, and this is the unit vector in the positive x direction. I'm just going to call it I hat. So if we draw the diagram again, E1 at x equals 3D points to the right, and E2 points to the left. And we have their magnitudes already found there. So now, since E1 points in the positive x direction that we defined, E1 will be positive. And then E2 will be negative. So this I hat means that this is multiplied in this direction. So I hat is this way. And it's a unit vector along here. And then E2 is pointing the other way. And now we can just factor out all the kq over d squared. And then this just becomes 1/9 minus 1/2. And it will be I hat for the direction. And if we simplify this, this becomes negative 7kq over 18d squared and I hat. And I hat denotes the positive x direction towards the right. And so since this sign is negative, that means the magnitude is just 7kq over 18d squared, and it's going to be pointing towards the left. And that is how you would solve this problem here.